Hi guys, I'm sorry I can't be there today, and it's been a long time since I've made a video, so I hope you'll excuse any errors. So today we're starting a new unit, which is 3.1, we're starting unit 3, and this is the first set of notes, 3.1, which is the transformations of quadratic functions. Now there's a couple of really cool things right here. Number one is that you've already done transformations before. We did them back in unit 1 with absolute value and linear functions. And so you're like, oh no, like I don't remember that. That's okay because it's at the beginning of a unit, it's really just a fresh start for you. Every new unit is a fresh start. So you have the opportunity to learn it right now. So the first thing that I want to do is I want to have you change this absolute value here. Change that to quadratic because I used similar set of notes because it's a very similar concept. So this is the quadratic parent function. So this right here, f of x equals x squared or y equals x squared is the general form of any quadratic function. It's the parent function, meaning every quadratic function looks to have the same shape. Now that shape is always just a U shape. That doesn't mean that it can't be wider or narrower or shifted in some way, but it'll always be a U. It's not going to suddenly turn into some other curve or a V shape like an absolute value. It's still going to take that general U shape. So the thing about transformations is that all transformations fall under 3 categories. And this is something that you want to know because we're going to apply these same transformations and these same rules to all different functions that we learn throughout this year. So, as I was saying, there's 3 categories: translations, reflections, and dilations. What you see on your screen right now is just translations. But every single one of those 3 can also be broken into 2 components. We have a vertical component and we have a horizontal component for each of those. So a translation is just a movement. So when I have a vertical translation, it's a movement up or down. So we're going to look at everything in function notation, because you can apply these same general rules to any type of function, which is why we have f of x. That f of x can be anything. So I can change that f of x right here. I can change this x squared to an absolute value of x. I can change it to x cubed. I can change it to any one of the parent functions, and it'll take place of the function that goes right here. So what does a vertical transformation look like in function notation? Well, what I'm going to see is I'm going to see addition or subtraction. I'm going to see a plus or minus outside of the function. And we're also going to write the word same. And I'll tell you why later, why we're writing the word same. But basically, notice I have my function right over here. And on the outside of that function is this addition and subtraction. Okay, so that's outside. So a plus k, when I see a plus k, that means this function has moved up. It's a movement up. So that's what I meant by same. When I see a plus sign, I expect movements up. And that's exactly what happens. It's the same. So when I see a minus sign, that means it's going to move down. So when I look over here, notice that this is my f of x. That is f of x, right? That's what equal signs mean. Equal sign means something is the same as something else. So when I see that f of x being with a 5 added onto it, I can see that it's on the outside of the function. So that tells me that this is a movement up. Now you can write out vertical translation up 5. You can write moves up 5, or you can just write up 5. Actually, I want to change the color on this one. Up 5. Now, notice that I have a minus 7 on the outside. It's the same sign. It does what we expect. And so we're going to say that this is a movement down 7. So all vertical transformations occur on the outside of the function because the vertical axis is the y-axis and I want to change the y values. All horizontal transformations occur inside the function. But the tricky part about horizontal translations is that they're usually not what you expect. So we're still going to see a plus or minus, but we're going to see it inside the function. And we're also going to write down the word opposite. So notice this time it's my input that's changing. So it's happening inside the function. It's my inputs. It's my x values that are being affected. Now, for it to be opposite is because when I see a plus h, I expect a movement to the right, but that's not what happens. A plus h actually means it's a movement to the left. And when I see a minus h, that's actually a movement to the right. So again, over here, notice that my parent function is x squared, but instead of only x being squared, this x is now an x plus 5 that's being squared. So that's what we mean by inside. And so this is going to be a movement left 5, which of course means this is a movement right 7. Okay, now let's talk about reflections. So again, every transformation has a vertical component and a horizontal component. So the vertical component is whenever it flips over the x-axis. So even though it's related to the x-axis, the transformation is still vertical because it goes from pointing up to pointing down. So that direction changes. This time, the notes that we're going to say is we are going to put that we want to multiply the entire function by -1. Okay, so notice I've got my function again. I've got my f of x, and I have a negative on the outside. All vertical transformations occur outside because it's the y values that are changing. So I'm going to take my function, and I'm going to multiply it by -1. So I'm going to distribute that -1 into my function. So again, remember my parent function was x squared. I take a -1 and I multiply it, which is how I get -x squared. Notice that this is on the outside. So this is a reflection over the x-axis. For my horizontal component, what I want to do is I want to not replace the entire function by x because this is going to occur on the inside, but rather I want to replace x with -x. So again, remember our normal function is f of x, and see how x is being replaced with -x. Okay. So notice that this negative sign is on the inside of the function. And notice that my input is -x instead of x. So look at the difference between this one and this one, right? In this one, the negative is on the inside, and then I square it. Whereas here, I squared it, and my negative was on the outside. So this is a reflection over the y-axis. And the third category of transformations are dilations. Dilations are probably what students struggle with the most. But again, there's a vertical component, and there's a horizontal component. And also, if you kind of understand the reflection component, you're going to understand dilations a little bit better as well. Because again, these are the vertical component is happening outside the function, and the horizontal component is happening inside the function. Now, the dilation is the category, and then a stretch or a shrink is the type that happens. So, just like before, for the reflection, we multiplied the entire function by a negative, by -1. This time we're going to multiply the entire function by a. Okay, what a? Well, this a right over here. It's going to be some factor, because whenever I increase something by a factor, I'm multiplying it, right? And so I have some factor that this function is changing by. So again, it's on the outside. And so I take that a and I distribute it into my function. Now, a note that I'm going to make is we are going to say ignore negatives when describing. Okay, because remember, the negative on the outside is a reflection. And then that number on the outside is the dilation component. So they do two separate things. The negative does a reflection, and then the value does a dilation. So over here, again, notice that my 5 is on the outside. And so this is a vertical dilation by a factor of 5. Now, if you go look at this in the graph, what's going to happen is you are going to see, if you graph the parent function, you're going to see a function that looks like this. That's the quadratic parent function. And then whenever I graph 5x squared, you're going to see a function that looks like this. Okay, so notice that that function got a lot narrower, but narrower is not specific enough here. Where we want to talk about in relation to that vertical piece. And so this is called a vertical stretch. Think about what happens to Play-Doh. If I stretch it vertically, it's going to collapse in on itself, right? So more specifically, this dilation is a stretch. Okay? Just like whenever I pull Play-Doh, it gets skinnier, right? Over here, again, it's on the outside. This is a vertical dilation by a factor of 1/5. And this time, it's a shrink. Man, I've said it backwards both times. Okay. So stretch here because it gets narrower, shrink here because it actually gets wider, which I know seems counterintuitive, which is why that direction is so important, okay? The vertical piece of it makes it really important. It helps you describe it more accurately. Now, horizontal stretches and shrinks are easily where students struggle the most. But you might not, and that would be amazing. And even if you do, that's also okay. We just come and we help each other, okay? So for a horizontal stretch or shrink, remember for the reflection component, we replaced every x with negative x. This time we're going to replace every x with ax. But that a is the reciprocal of the factor. Okay, this part is the part that students get confused. So here's what I mean. If I have a factor of 3, then my A value is actually 1/3. That's how reciprocals work. If I have a factor of 2/5, then my A value is 5/2. Okay? So, right here when it says AX, you substitute it in exactly as you see it, but your description is going to be the reciprocal. So again, notice that this is on the inside. And I want to have my input is AX instead of X. So notice that this was normally X squared, but I'm replacing X with 5X. So pay attention to where those parentheses are because it's really important. So this is inside. So here's how you describe it. This is a horizontal dilation by a factor of 1/5. See how it's the reciprocal of the factor? Okay, by a factor of 1/5. So just like whenever we were looking at the graph earlier, if I was to graph this, this would be my quadratic parent function. And this is actually the graph that it would create. It would create a real narrow graph. And you're like, well, that's exactly what a vertical stretch was. That's why the functions are so important to pay attention to. Because that's what the equation is, because you can't always tell on a graph, okay? But again, this is why the direction is also important, because now I'm looking at it from a horizontal perspective. So that same thing, like I was saying, I'm grabbing the Play-Doh, but instead of me holding it at the top and the bottom, I want to hold it at the left and right. So now I want to see, okay, how do I turn it into this purple graph? And so that's going to make this a shrink. It is a horizontal shrink. So that's why that vertical and horizontal piece is so, so important. Same thing here. I'm on the inside. So this is going to be a horizontal dilation by a factor of, again, I want reciprocal, so 5, and that makes this a horizontal stretch. Okay, really important that you pay attention to the direction of that transformation. Is it vertical or horizontal? Because that's going to help you decide based on looking at that graph. All right, so from here, I'm actually only just going to do one of them, and then I'll give you the answers to the others so you can pay attention to them. But I'm actually going to go through all the way on one of them. And the one that I'm going to go through is problem number 5, which you're lucky because this one has the most pieces. So when you're looking at number 5 right over here, I want you to pause this video and I want you to think about how many transformations there are. Now, the way that you want to make that decision is by looking here at the parent function and looking at the new function that they've given me. And I just want to visually look at what looks different. How many things look different? So pause the video here and think about that. So when I look, there's a very clear one right here. I see a -1 on the outside. I see a +4 on the inside. And this right here is where students get the part wrong, okay? They say 3 because they see 3 different numbers, which would normally be really good, right? We're paying attention to how -5 and 5 are not the same thing. However, if you remember from the front, this value does a transformation, and actually this sign does a transformation. One of them is a reflection and the other one describes the stretch and shrink. But let's do the red and green first. I have this red on the outside And anytime I'm on the outside, it's a vertical transformation. And since I'm adding or subtracting, that makes it a translation. So this is a vertical translation down 1. Now, again, if you just put down 1, that would be fine because it's all in the vertical translation part. This one right over here, this plus 4, it's on the inside. That makes it horizontal. I'm adding or subtracting. That makes it a translation. However, because it's horizontal, it's going to be the opposite. So I see a plus, which means it's going to be the opposite. It's going to be left. So this is a horizontal translation, left 4. Now these last two, this one right over here, it's a negative sign, but it's on the inside and it's being multiplied. That makes this a reflection over the y-axis. Okay, it's a reflection over the y-axis because it's on the inside. It's a horizontal transformation. And this one right over here is a vertical dilation by a factor and finally we have this last transformation on this 5. It's on the inside, so that makes it horizontal. It's a dilation, but more specifically it's a shrink by a factor of, I hope you said 1/5, because for those horizontal dilations, we want to use the reciprocal of the factor in the function. So pause the video, go try 1, 2, 3, and 4, and when you unpause, the answers will be on your screen. All right, take a look at the answers. And then pay attention to, if you missed any, be paying attention to what types of parts you're missing. Are you always missing the dilations? Are you always missing the vertical transformations? Be paying attention to those things. Now, the last part is taking a description and then using that description to write a function. So we're essentially going backwards, right? Normally, we're given the function and we provide the description. Well, this time, they're providing the description and we create the function. So I'm only going to do number 7. And then again, I'll put the answers to 6 and 8 on the screen. And then you can come up with make sure that you're able to come up with the way to do it. So f of x is equal to x squared minus 5x. I want to do a translation 3 units to the right. I want to go 2 units up. And I want to reflect in the y-axis. Okay? So I have my original function, and this is where our function notation that's on the front really comes in handy. So I have my original function, x squared minus 5x. And it's like, okay, how do I do a translation 3 units to the right? Well, when I look at the front of my notes, I see that it shows me this right over here. Okay? So that is what's going to happen to f. Now, if I want to go 3 units to the right, we know that instead of a plus or minus h, I specifically want to do a minus 3. That's what I want. And so instead of x, I actually want x minus 3. So this tells me replace x with x minus 3. So I have f of x minus 3. So basically everywhere I see an x, I'm going to replace it with x minus 3. So I see an x here, so I'm going to replace it with x minus 3. Notice that the squared is on the outside of the parentheses because I only want to replace the x. Minus 5, and then x minus 3 again. Now, you could totally go in and distribute all of that stuff. Okay, you can do x minus 3 times x minus 3 to square it. distribute the -5, combine your like terms. You can 100% do that. We're just not going to do that. Now I need to ask myself, am I done? Well, of course not. I've got 2 more transformations to do. So what that means is this is not the g function because I'm not done with this problem. It's now going to be called some new function, some intermediate function that I am now going to use to get to the next step. And you can call it whatever you want. I'm going to call it O of x because I'm using orange. Okay? So now when I do this transformation, it's going to happen to this function, this O function. So I want to take the O function and I want to move it up 2 units. So again, I'm going to go back to the front, and that says f of x plus or minus k. Okay, well this time my k is 2. And I don't have an f of x, I have an O of x. So that's exactly what I'm going to write down right here. O of x plus 2. And now everywhere, I'm going to take my O of x function, which is x minus 3 squared. And actually, let me keep the blue right here to show that that's the new transformation that's occurring. Minus 5 times x minus 3. And I just want to tack a plus 2. So I want to take this whole function and I want to add 2 to it. It's not like terms with anything, which is why I just put it on the end there. Again, this is not my final function because I'm not done with my transformations. So I'm just going to call this b of x. And this last transformation that's occurring is going to occur on b of x, which is a reflection in the y-axis. So again, in my notes, I look and I see I do a reflection of the y-axis by doing f of negative x. Well, it's not f this time, it's b that I'm trying to manipulate. Okay? So my next line is going to be b of negative x. So I am just replacing all of my x's with negative x. So here I'm going to replace x with negative x minus 3 squared minus 5. Again, I want to replace x with negative x minus 3 plus 2. Now I've done my final transformation, which means I can finally call this g, and I'm going to drop all of those extraneous parentheses. So g of x, oh, and it worked out because I used green, is equal to negative x minus 3 squared minus 5 times negative x minus 3 plus 2. So the procedure, if you just take it step by step using the function notation that we have on the front, it's going to be a lot easier. Just really use that function notation. So again, we took the f function and we translated it into this orange function. Then we took the orange function and we performed this transformation on it. And then we took the blue function and we performed this transformation on it. So that's basically how I went step by step by step. Okay, so you can kind of see the way that we're moving from one function into the other. Again, pause the video, go try number 6 and number 8, and then come back so you can see how it's done. All right, here are the answers to number 6 and number 8. If on number 6 you have a bunch of stuff with, like, you have an 8 out here, and then you have this right here, and then you have a negative, that's just because you didn't simplify. If you have something that looks like this, you just didn't simplify, because 1/2 x squared is equal to 1/4 x squared. And then I distribute that negative 8 into it, and that's how I get negative 2. So if you're confused, you're like, oh my goodness, I don't have any of that. It's just because you didn't simplify. And then you're like, well, you didn't simplify on number 7. I know I didn't. It's just because that's a much more complicated simplification, and I want you guys to have more practice doing those first. All right, see y'all later.